Hello students, this video lecture will cover section 7.4, Similarity in Right Triangles. By the end of this lesson, you'll be able to find and use relationships in similar right triangles. The primary focus of this entire lesson is on the following theorem. It states that the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So here we can see we start with triangle ABC, which here is identified in purple. Then we draw the altitude C to D, and remember an altitude is a segment that connects a vertex to the opposite side at a 90-degree angle. We can see here that triangle ABC is a right triangle with right angle at angle ACB, and CD is that altitude that we just spoke about. The theorem then tells us that triangle ABC is similar to triangle ACD, that triangle ABC is similar to triangle CBD, and finally that triangle ACD is similar to triangle CBD. So our first problem asks us to identify similar triangles. It says, what similarity statement can you write relating the three triangles in the diagram? So let's start by color coding the triangles. By adding some color to the diagram, frequently we can see things that we wouldn't see otherwise. So here you can see I've dragged the large triangle, triangle QRP, off of the diagram to separate it. Let's continue doing the same for each of the other triangles. Now I've dragged triangle QSP off of the diagram, but you can see its orientation doesn't match triangle QRP. So let's go ahead and rotate it into place. You can see that rotating this triangle doesn't really get us what we're looking for, so we need to include a flip. Now we have it where we want it. We have triangle QPS in the same orientation as triangle QRP. Let's just tidy up our vertices a little bit. And we have one final triangle to deal with, triangle PSR. Once again, by dragging the triangle off of the others, we can see that it's not in the correct orientation. So let's try rotating it. Again, the rotation doesn't get us exactly what we're looking for, so let's try flipping the triangle as well. There it is. Now we have all three triangles in the same orientation. So once again, let's tidy up the vertices. And now let's write our similarity statement. From our separated diagram, we can see that triangle QRP, I'm talking about the purple triangle here, is similar to triangle QPS, this is the red triangle, which is also similar to triangle PRS, and that's the orange triangle. So now we have the similarity statement relating all three triangles in the diagram that we started with. This theorem has two corollaries, and for the two corollaries we need some new vocabulary. Proportions, where the means are equal, occur frequently in geometry, so they're given a special title. We say that for any two positive numbers a and b, the geometric mean is the positive number x such that the below proportion is satisfied. So here we have a over x equals x over b. So x is the geometric mean of a and b. So let's look at finding the geometric mean. Question number 2. What is the geometric mean of 4 and 18? So to set this question up, we set 4 over x equal to x over 18. The cross products property tells us that x times x has to equal 4 times 18. Simplifying the left-hand side of this equation, we get x squared equals 4 times 18, which is 72. So to solve, we take the square root of both sides. We have the square root of x squared equals the square root of 72. The square root of x squared is positive or negative x. But if we remember back to our definition of the geometric mean, we're told that the geometric mean is the positive number x. So let's simplify the square root. We have the square root of 72, which we know is 4 times 18. So 4 can be written as 2 times 2, and 18 can be written as 2 times 9, which is 3 times 3. So simplifying square roots, we get to take the pairs out, so we have one pair of 2's. We have one pair of 3's. And the square root of 2 gets to stay inside. So in this case we have x equals 2 times 3 times the square root of 2, or x equals 6 times the square root of 2. So 6 times the square root of 2 is the geometric mean of 4 and 18. So our first corollary states that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So in this case we can see that if we take 2 over 4, that's going to be the same as 4 over 8. And the example's worked out here for us. 2/4 reduces to 1/2, and 4/8 also reduces to 1/2. Our second corollary actually yields two different formulas. It states that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. So here we can see that AB over AC equals AC over AD, and AB over CB equals CB over DB. So we'll take a closer look at these formulas in just a second. So here's a detailed diagram labeling all the parts of one such triangle and the formulas for each of the two corollaries. Please take the time to copy this picture and these formulas down on a 3x5 card and have it available for class tomorrow. So our third question asks us to use the corollaries to find the values of x and y. So this is one of the situations where I would use my 3x5 card. So I take the picture on my 3x5 card and I try to rotate it so that it matches the picture in the diagram. Then I try to identify which part is which. So in this case you can see that the 4 matches the S1. So I'm going to write down that S1 equals 4. I can see that the 5 is the same as S2, so I'm going to write down S2 equals 5. The altitude in this case is y, so I'm going to write down that A equals y. And L1 here pairs up with x, so I'm going to write down that L1 equals x. So if I try to fill in corollary 1, I have S1, which is 4, over A, which is y, equals A, which is y, over S2, which is 5. So cross multiplication in this case, I have y times y, which is y squared, equals 4 times 5, which is 20. And if I take the square root of both sides, I get y equals the square root of 20. And since I know that that's 4 times 5, I'm going to write this as 2 times 2 times 5. And I'm going to pull the pair of 2's outside, so I'm going to say that y equals 2 times the square root of 5. Now you can see here I have L1 but I do not have L2, so when I use corollary 2 I'm only going to be concerned with the left-hand formula. But in this case I have a problem because one of the two formulas asks for h. I don't have h anywhere here, but if I look, h is the combination of S1 plus S2 using the segment addition postulate. So I do actually have h, it's this entire length here, which is 9. So the proportion I'm going to set up here is h, 9, over L1, which is x, equals L1, which is x, over S1, which is 4. And once again, we cross multiply, so we get x times x, which is x squared, which equals 9 times 4, which is 36. And taking the square root of both sides, we see that x equals the square root of 36, which is 6. So by using the formulas on our 3x5 card, we were able to solve this question fairly easily. So our final question of the day is a word problem. We're preparing for a robotics competition using the setup shown here. Points A, B, and C are located so that the length from A to B equals 20 inches. Segment AC is perpendicular to segment DB. Point D is located on segment AC so that DC equals 9 inches. It's our job to program the robot to move from A to D, pick up a plastic bottle, and then move to point B to drop it in the recycling bin. And in order to do this, we need to know how far the robot has to travel from D to B. So again here, I'm going to use the 3x5 card that we set up earlier. Now our 3x5 card is an imperfect orientation, so let's rotate it. By rotating our 3x5 card, we get a better idea of what each location represents. So we can see here, this is now L2, this is L1, this is S1, this is S2, the entire length there is H, and the altitude is A. So here we're asked, how far does the robot have to travel from D to B? So in this case, we're trying to find the value of A. So let's move our 3x5 card down here. We can see that corollary 1 is the only formula that has A in it. So in this case, we only need the values of S1 and S2. So those values here are 16 and 9. So let's set up that proportion. We have S1, which is 16, over A, which equals A over 9. Cross multiplication, we have A times A, which gives us A squared, which equals 16 times 9, which is 144. Taking the square root of both sides, we get A equals 12. So this distance is 12 inches. Now that we know the exact distance, we can program our robot. So that concludes section 7.4, Similarity in Right Triangles. Thanks for your attention, and I'll see you soon.